Awesome. It's all your share.
Oh, nice. Now everyone can see us as well. Good stuff. Awesome. Thanks everyone for joining. So yeah, today I will talk through this paper, Analyzing Transformers in Embedding Space. So the reason I picked this paper is I enjoy a chance to review transformers because we don't look at transformers enough, of course. But secondly, I thought it presented like quite an interesting perspective on how to interpret like what transformers are doing, and presents this kind of like generalized framework for like mapping the parameters that are being learned in transformers to the embedding space, where then we can make like interpretations about what kind of relationships are transformers learning and what are they doing under the hood. This paper actually extends on a few other papers that projected like the parameters of some of the components of a transformer model to the embedding space, and we're able to make some conclusions about like how it's learning across time and like what it's learning. So this builds on that and presents a sort of more generalized framework on which to do that. I thought it'd be a useful recap to kind of go over like what is a transformer model, like a little bit for those who could use the recap. I know I could use it before I read the paper. Transformer models, I guess, are, and obviously if anyone, please feel free to correct me, but this is my interpretation. So you have like an input sequence, which you project to like an embedding space. You also encode like the positions of the tokens as well in that initial, in that sort of input to the first layer. And then it's composed of sort of two parts, the kind of like encoder decoder parts. So in terms of like encoding, so each block sort of does like a couple of things. So the first is like it splits the input sequence. So imagine you have like n tokens, and the n tokens you map into an embedding space of like d dimensions. It splits them and then performs attention across like all of the input tokens. And then it passes also like this is important as well. So it like does the attention, and then it also passes the initial input as well through this like residual connection. And then it applies two like feed forward layers. And it sort of does this repeatedly, and then also does it in sort of the decoder side. So you pass the embeddings, and then it decodes into the output probabilities. So I guess like the two key components we'll talk about are like the attention layers and then the feed forward layers, which are sort of repeated across like all of the transformer models. So we can go back to the paper. Can everyone see that okay? Yeah. So yeah, as I mentioned, this work they sort of present the whole purpose of like this paper is to like project all of the parameters from transformer models into the embedding space, which is the space that maps like all of the vocabulary items for all of your text. So what do they actually do in this paper? So they derive this sort of framework of how to do it, which we'll talk through. Then they, as a result of doing that, they can then do a few things that I think are really cool. So first is like, you can basically show that you can interpret the parameters of the transformer models in an embedding space, which then allows you to, for example, like compare and align like two different models to show like that share the same vocabulary, to show that they're aligned, that there's sort of stability in the learning, that they're not learning wildly different things. So you can interpret the parameters of two models trained on the same vocabulary. But also really cool, you can do this thing called stitching, which allows you to construct a new classifier for a new task without actually training on any data by taking the parameters from one and projecting across the embedding space to the other model. But we'll sort of dive into those. So I guess the interesting sort of value that this paper adds is that previously, like, interpretation methods for transformers have been restricted to passing like input data and seeing what happens. So it relies on kind of like feeding inputs to the model and analyzing what gets activated and making interpretations of that. This is like a zero-shot method of doing that. So you effectively, you don't pass any data, you're interpreting the parameters directly after training. So there's this bottom here, I think part is interesting. So the paragraph at the bottom. So in the previous paper that I mentioned, they showed that you can project like hidden states in the feed-forward part of the transformers to the embedding space via the embedding matrix. And you can extend this to like other parts of the model. So for example, if we consider like the attention, so if you look here on the left, so if you have like a feed forward layers where you have like the hidden states, you can project it using like the embedding space. But where you have like the key value, like output weights of the attention matrix, you can actually you can do some interesting algebraic leaps to basically get you to a point where you can think of mapping the interaction between the query and the keys and the values, for example, to as like interactions between tokens or interactions between vocabulary items. So this is like the extension that this paper adds. So we'll look at it. We'll look at it a bit more as we like kind of go through. But yeah, so I guess what they introduce here is that like the kind of applications I mentioned. So they look at like what happens when you fine-tune like a pre-trained language model on, like, for example, a sentiment analysis task. You can project like the changes in the parameters as well in the embedding space. So you can start to understand like what is it learning and how is it learning. So you actually start to see that the changes in parameters relate to like sentiment being learned. So the change in the vectors can be mapped as like words or close to like words that represent sentiment. And then we'll also look at stitching. But yeah, the code is also available if you don't have to play around with it. I haven't had a chance to play around with it. So as I mentioned, the transformer models are made up of these kind of different parts. So there's the attention module, the feed forward module, and the embedding matrix. So as I mentioned, the attention module basically takes like the input sequence and then is parameterized by these 4 matrices. So it's the query, keys, values, and outputs. So the input is basically projected to produce these like queries, keys, and values using these like parameters, and then that's fed into like the attention layer. And so we'll look a little bit into like these parameters, which is the things that we want to project into the embedding space. Then there's the feed forward module, which is like a 2-layer feed forward. And I thought it was kind of interesting. It's not new. I think they refer to these 2 papers, but they basically say that you can interpret the feed forward module also as like keys and values. So if you think of the first layer are like the keys and the second layer are the values. So you can apply this kind of like algebraically, basically.
But it's a multiplication.
Because a multiplication, yeah.
How about so you can interpret it as how about the non-linearity?
with the non-linearity applied to it. So you can see if they kind of like say like this is how you can think of like the feed forward.
Okay, so that is okay. Okay.
Yeah.
Sure, everything is a feed forward.
Yeah, exactly. And then there's the embedding matrix. So the way they look at like transformer models, I think is kind of interesting for this purpose. So they look at they interpret transformer models in this method that they call like a residual stream. So what that means is like if you think of each layer, it takes an input which is like an embedded sequence of tokens and adds like information to it at each stage. And this information is passed like through all of the different layers. And so you can see like you can think of like then every layer as like you can as like steps in the transformer that's adding information to it. And so you can project like what's happening at each stage into the embedding space to try to like understand basically like what's happening.
This is referencing the fact that you are doing something with the original input to the attention layer, right? You bring it back in.
Yeah.
Okay. Mm-hmm. Is it thumb? Is it just a thumb usually? The attention layer?
Yeah, I think so. Yeah. It just does this. This is the original input.
Right. Yeah.
And I think that's it. Yeah. This is like the attention multiplied by this like output weights.
Okay.
Then if you remember, so you can think of like the feed forward like weights as like you can project them into the embedding space. I think the interesting parts really I think are if you consider if you rework the softmax basically to say, okay, so rather than looking at like these projection matrices in the attention layer, you can define these interaction matrices between these parameters. So you have like WQK, which is like the basically multiplying the query and the key projections and the value output. And so then what they say is this kind of encodes the amount of attention you apply like between tokens. And so then you can look at everything in terms of like interactions between tokens. So this becomes quite useful because then when you're projecting stuff into the embedding space, you can kind of interpret this as like rather than projecting to like one vocabulary item, you're projecting like the interaction between different vocabulary items, and you can see where it's most activated. You can see like there's some interesting interactions going on there. So then they kind of go into then like a little bit, you know, how do they project the parameters into the embedding space? I think it's not, maybe this is probably not the most interesting part of the paper necessarily, but it's, you know, interesting like background to talk about like how do they project. And I think the interesting thing is like the way they like project it and then into embedding space and then project it back is using like the right inverse, but instead here they use the transpose of the embedding matrix instead of the exact like inverse of the right inverse of the embedding matrix.
Can you argue that the embedding matrix is orthogonal? So you normalize in terms of yeah, I guess if the feature dimension is small enough, right? Could be orthogonal? No?
Yeah, maybe.
So do they Yeah, but it should be good enough for approximation. Right?
Yeah, that's kind of what they say, is it works good enough.
Yeah, it makes sense why. Yeah.
Yeah. So yeah, what they do is they, in terms of like the experiments they do. So the first is like they try to do the simple task of like interpreting the parameters in a GPT-2 model. So what they do is they take the, for example, like the transition, one of the transition matrices, and then examine the top K pairs of vocabulary items. And they present in the appendix like what here. What comes out. So what I interpret from this, and I'm not entirely sure, like I fully got this, but basically they, what I gather is that they project into this like embedding space, so like this interaction space, and then they when they say they look at the top K, I assume they look at like the highest like activations, and then interpret like what, when you projected what, like what parts of the vocabulary does that correspond to?
Is it during training? I didn't.
So they train, it's pre-trained,
Yeah.
and then they do it on that. So it has been,
After they continue training on the GPT model.
yeah,
They're trying to interpret the training of.
Yeah.
So I don't think there's any more examples in which they train. They're just looking at like all of the training parameters in the matrix.
I was just wondering because training GPT model isn't trivial in terms of size.
yeah. So I assume they take an already like pre-trained one, and they examine that one.
Yeah, but if it's pre-trained, how do they have access to the activations?
Maybe they, when you say not trivial, it's like these people couldn't do it themselves.
No, they look at the interaction matrix between. So
I think what Valen's getting at is like, how do they have access to that matrix? Because
Also, yeah,
so
exactly.
is it you trained it as
Yeah.
well?
Also, is GPT-2 open source?
GPT-2 is open source.
Okay.
Yeah.
Maybe it's open source, and this data also.
Yeah.
Training data. Okay.
Yeah.
Because a lot of times they say we use Wikipedia, so then what exactly, right? So
No, I think they use like they can access like all the weights.
okay, well, weights, yes, but to get access to that matrix, the activations, you need to actually train it. Unless GPT reported, because those are during, so those matrices change during training, right?
Yeah.
For each equal, for each part, you get different matrix. All right.
Well, I'm not sure what you mean.
I was just wondering if they actually trained the model from scratch. But they probably did. Did they say that?
No, they don't mention anything about training from scratch. They say they take GPT-2 medium, which is already like open source.
They said okay pairs of vocabulary items. Okay.
What are rows of one of those matrices, the embedding matrix, they refer to a vocabulary item?
Yeah.
Okay.
Yeah, exactly. Yeah, so when they say top K pairs of vocabulary items, so this interaction matrix. So this is what's learned in training, right? And so now it's been trained, and now they have like this this matrix available to them.
I see. So the matrix is after training, and the embedding matrices are also after training, so they don't need access during training.
Yeah, I think
that
so.
that makes sense, right? That's what I was.
Yeah, I don't think so. Yeah, it's all after training. But what's kind of interesting is, So each head kind of focuses, they find that they kind of do slightly different things. This is good. I don't know.
I think we saw in another paper also that heads have different impacts,
Yeah,
and then some of them are actually useless. So a lot of times you can actually after training you can drop some of the heads.
drop the heads.
Yeah, but you don't know which ones. So you have to start with many heads. Well, the 16 heads, yeah.
No, it's like loads of them.
Yeah.
So
many layers.
I forget how many.
Plus 16 per layer.
Yeah, per layer, yeah.
And then when you look at them, a lot of times you can drop them and keep maybe two, but you don't know which, like what to keep before you train.
Yeah.
Is that,
So, sorry.
I guess I was just going to ask, is there some kind of rationalization to this? Is it like these are the sorts of pairs these heads are paying most attention to?
Yeah, so I think it's like,
Attention as in,
Yeah.
attention is a score, right?
Mhm.
So the score between two vocabulary items, two
Mhm.
words or can be parts of words, right? If you look
Yeah.
at it. The score is high between them,
Yes.
and that's what the attention is learning.
Mhm.
yeah,
And they can have, you can interpret them in different ways, because sometimes it can mean the king and queen are similar, other times can be king and husband are similar. So it's like different functions, right?
so basically effectively it's like when these two are present, like they attend to each other quite
Mhm.
heavily.
Mhm.
These tokens at these tags, right? So you have
layer 22 and 13, it's just the
and these, yeah. And then there's like some layers that map to, yeah, to gender, to geography.
Also, it's different.
British spelling.
So is it the two different heads behave differently in different layers?
Looks, that's a good question. I don't know. I don't know if they look at the same heads in different layers.
It's actually interesting to print out everything.
Yeah.
Okay.
And then they look at the query key, so look at different types of matrices as well. Um,
What do they say about that? They just say yeah.
Okay, so that's about interpreting attention.
yeah.
Okay.
So this is interpreting attention.
Mhm.
Then this part I don't fully understand what they're trying to do here.
Oh. Yeah, it seems to be like very post-factum. Like,
Yeah, right. They kind of
yeah.
just like,
Yeah.
oh, we're gonna pick some of them that suit our. I think these ones are kind of interesting. So they take like a certain topic. So let's say like measurements,
Mhm.
and then average their embeddings, and then they look at like all of the feed forwards for different layers and find like where in the model like are we learning these things, like what's the ones that are most like similar to this. They do it with a couple of different topics. So they, for example, they feed like the average embedding for Python, Java, JavaScript, and so they find this layer in layer 14, the feed forward, where like it gets activated quite high, and they find like all these different methods with it. Yeah.
There is Unix, Linux, but no Windows. Right? So,
Now Windows up here.
there is, oh yeah, nice.
How are they making? What's the making? Then
So
you say, what is like the highest activation
yeah,
dimension
I think so.
across the whole?
Across all different layers. Yeah. Yeah.
Interesting. Well, this shows that there is a low level dimension where all the programming languages and file systems are close to each other, right? Because when you average, if they are not in the same hyperspace, then they wouldn't be close to similar item section, right? You could basically you can find a low dimension space where all the computer related things stay.
Yeah.
I think that makes sense. Useful.
Cool. So that's the kind of like first thing. Part I thought was really interesting. So they so first they take the pre-trained model and they say, cool, can we interpret the parameters in this pre-trained model? So it's just out of the box GPT-2. Then they say, okay, what happens if we fine-tune the model on a certain task? Can we interpret the changes in the parameters as well? Can we project the changes in parameters to the embedding space and make some kind of assumption or like interpretation about what's happening to those parameters? So they take like the top 3 layers and then apply like a sequence classification on IMDb basically sentiment, so positive, negative sentiment on IMDb reviews. And then they look at the difference between the original parameters and the fine-tuned model in those 3 layers. So what they find is that, interestingly, in some cases, and again, they cherry pick cases, which I think is probably one of the like negative points of this paper, because it just feels like they can just cherry pick examples that suit their needs. But the difference in the parameter changes, or the negative difference, is projected to things that express sentiment. So if I look at appendix C, you can see some examples. This section contains abusive language. I'm sorry if anyone's offended by this. So
Only for scientific purposes.
oh, yeah, exactly, only for scientific purposes.
What's GI?
Where are you looking?
Oh, CGI is the cosmic.
CGI.
Is that interesting?
Yeah. So yeah, basically what they do is they look at like the fine-tuning vector for well, which vector do they take to the label positive and this label negative?
What do you mean?
So it says,
For the whole sentence, right?
sorry?
It means the embedding for the whole description.
Say that.
What do you mean? What vector do they take?
So we show the fine-tuning vector of the classifier weight. So is that the final layer?
So that's the extra one that they use up. So that there is the fine-tuning means after pre-train, right? There's a pre-train embedding, and then
Yeah,
for fine-tuning they get a new, I guess, a new embedding vector.
yeah. Yeah.
So they take that.
Yeah. Okay. And then they do the same thing, but they look at different they look at like different like so the fine-tuned layers. And yeah, they present the ones that seem to contain relevant patterns. But yeah, they showed like the positive difference and the negative difference of like the difference in the fine-tuning. You can kind of see like what things come up in those.
I think it's kind of cool. It is fun, yeah.
So clearly, basically, the point it's trying to make is that when you fine tune the last layers, you can actually interpret like the changes in the parameters. So it'd be quite interesting if we fine tune on like, if you have a data set and you fine tune to see like what kind of things is it like, is it learning at those last layers, or was it changing? So that was like the first part where they kind of interpret. So they take one model and they interpret the parameters. The second thing they look at is they say, cool, what happens if we have two models and those models share the same vocabulary and tokenizer? What can we say about those two models, and can we like align the parameter vectors and like compare the models basically? So in this case, sorry,
Different architectures.
no, same architectures, I think, because they compare like the same layers, like same parameters in both
Range of the
models.
same data.
Yeah, with different random seeds.
Ah, so the random seeds are okay.
Yeah, so they look at like multi-BERT, but initialized from different random seeds.
Okay.
And yeah, what they do is they basically take like two models and they compute the correlation between like the projected, the parameters projected into embedding space. So they create kind of like a similarity matrix for each layer. And they look at like, then they say, sorry, yeah. So then given the similarity matrix between like, let's say all of the layers of one model and all of the layers of another model, they try to see like, okay, which layer is most similar to another layer in the model. And so this is kind of what comes up. So when you align in the embedding space, the layers kind of correspond like one-to-one, which is interesting. So effectively what they're saying is when you project the parameters into the embedding space, you can actually, there's some stability in like one layer in one model is like most similar, has the most similar activations to like a layer in another model, or most similar interactions. Whereas what they're saying is if you were to look at like just the feature space, then you wouldn't be able to make any such claim. Like it doesn't seem to, you wouldn't be able to make the same case for like alignment. And I think where this is useful, or at least where I thought it was useful, is like you can start to, if you have like the same model and you train on different random seeds, it's kind of like a way of understanding like, are my models like stable in some way?
Can I ask a question? What's feature space?
What I assume here is basically they compare the parameter vectors, but not projected to the embedding space. So I think what they mean by feature space is just like the space of the inputs at each layer for each parameters.
So the one what embedding from the vocabulary.
No, so while each layer takes like the input from the previous layer. So that's the feature space of that layer.
Ah, I see. Okay.
Yeah.
Alignment. Maybe that's a stupid more question.
Oh,
Correlation between the projections and the event.
it's like 2 second diagonal.
Yeah.
So basically, the layer, each layer organizes features.
Mm-hmm.
You know, yeah. Maybe.
So I think alignment here basically means like I think what it means is just basically like the layers match in in the parameters, or like there's a correlation between the parameters basically at different layers.
Okay.
The problem is that if you look correlations purely in the parameters in that space, then it gives you seemingly sort of random like alignment between layers. But the correlation, if you project it, because what I assume is each learn, because the embeddings, the matrix is learned, right?
Yeah.
So they're effectively going to be different. So it kind of shows you that like we can actually start to look at layer correlation, but at the embedding space makes sense, not at the parameter space.
You're mapping to the same space as well, right?
It's the same vocabulary. Yeah.
Okay.
So it's the same dimension. Yeah.
Interesting.
The last thing they look at is this thing called stitching. So the idea basically is like, can we use the parameters of one model to basically to have like another model? Well, yeah. Sorry, let me say it again. So you have like a fine-tuned model, and can you stitch like some of the parameters of those to another completely pre-trained model, but one that hasn't been fine-tuned, and still achieve like good accuracy?
Possibly, right? Because it's the same architecture, same data,
Yeah,
same
And-
parameters, I guess.
Yeah.
Obviously.
exactly. And so what they do effectively is they say like, so where's the setup? Actually, oh, yeah, here. So they have two models. They have like a 24-layer GPT-2 medium and a 12-layer GPT-2 base model. What they do is they fine-tune the last 3 layers of model B. And then they take the hidden states and they multiply the hidden states by this kernel, where effectively it's like this kernel is kind of like what it's doing is it's projecting first into the embedding space of your own model, and then it's projecting back into like using the embedding matrix of the other model. It's kind of projecting into the embedding space and back again to the other model. So the idea is like if you were to just like take the parameters from one model and just like stitch them into the other model, it would do a crap job. Because as we've seen, like they sort of learn differently based on initializations and based on lots of different things. But if you now like project into the embedding space first, to take like the fine-tuned model and then stitch it into the other model, then you can achieve some interesting results, but not consistent. So these results are a little bit iffy.
Is it because the kernel is linear?
Sorry?
Is it because the kernel is linear? Maybe because of the transformation between the two models is not linear, right? Because you're multiplying by a matrix and another matrix.
Yeah.
Maybe there has to be some more advanced.
So you think it loses something on the way, or?
Maybe, right? Yeah. Why would you assume that there is a linear marking between the two models?
Well, I guess if you're going via the vocabulary space, there should be, right? Or no?
I don't know, those are highly nonlinear, complicated models. What they learn, why would they learn spaces that can be marked with a linear marking?
Fair enough.
Anyway.
Yeah, interesting.
Yeah.
Saying 3 models with higher math.
Yeah, I know, right? So they did it 11 times, but they took the 3 that looked the best.
There.
And I think I'm trying to figure out what they do here. So it's a 24 layer model. I think what they do is they take the fine tuned. They take the last 3 layers of model B and basically apply them on top of like layer 0, 1, 2, 3, like on top of different layers in model A, and then seeing like what's the accuracy.
I guess it doesn't cost them anymore, right? Like everything's trained at that point, so.
Yeah, exactly. So I suppose what it's saying here is there is value in like what it's learning across the way on each of the different layers.
That is interesting, isn't it? Is that the slope down at the end, I guess you could kind of interpret as by the time it gets to the end of the 24, it's starting to specialize somehow to the task that you had originally trained model A for. So
why does it drop afterwards?
yeah, so perhaps those internal representations are too specialized, whereas the internal representations earlier are still able to be brought up again.
And wavy interpretation of the graph, but
No, I agree though, I think. I mean, it'd be nice to see the other 8 lines. But yeah, so that's basically what they look at. They mention a few limitations. So one is that they look at everything through the vocabulary lens. I think that's kind of okay. They mentioned that they use like E transpose instead of E prime. That they say that like there might be different variants of embedding matrix that improve performance.
No, they do use the transform mostly in the embedding part, right? Because they do E times E transpose.
Yeah,
Do they use it as a replacement for the right inverse?
they do that in the projection to the embedding space.
Yeah, but also they also do it here in stuff experiment.
Yeah, I think so. Yeah. Yeah, so that's the paper. They have a deep appendix, but mainly because they copy like all of the examples, which I think are quite amusing to look at.
I always find it interesting when people study the model itself, because
Yeah,
it's much harder, because you can say, I can explain you what my brain does. No, I can explain you what I think, but I can't explain you how my brain operates. Right? You can look at the result and explain that, but it's really hard to analyze the details of the model.
yeah,
And they're trying to do that here, right? Which is
yeah.
a difficult task. Well, right?
is there a like is there an official field of interpretability as separate to explainability? Like is that different?
I guess you could say that, because interpretability would be I don't know, maybe. Is it different?
I don't know. I guess they're not trying to explain why it's come to a particular answer. They're like trying to interpret what is going on inside when it's doing. So I think the flavors of the same thing, I think, but slightly different.
Yeah, it sounds like they're trying to interpret like specifically at each different like layer, so layers in different heads. Like, can we make sense of like what it's trying to do and like what are the interactions it's learning?
So, just for my benefit, somewhere there's a huge long vector of vocabulary, right?
Matrix. What do you mean?
Well, there's like a dimension along which the entire vocabulary is populated, right?
100,000 words in the vocabulary, and then for each we would have one whole vector to start with, and then you kind of that.
Is a lot helped here by the fact that the internal representation stays the same dimension the whole way. Like you wouldn't be able to use the same. You wouldn't be able to use the same matrix. Yeah, if there was some model where the internal representation changed size, you couldn't use the same matrix to get out.
What do you mean internal representation? The hidden layers I mentioned.
Basically, like
Yes,
what comes out of each layer.
Yeah, because it's a repetition of the same tension.
Yeah, exactly.
And that's the interesting part of the residual stream. Of why it makes sense to do it, because like they sort of see each layer as like we're adding information to the input, which you kind of like attending on the input. You're saying like this is interesting, or like, oh, that's interesting. I mean, in a very like in a very hand wavy way. I actually thought an interesting use case for this might be in tackling like bias in models. If you can look at the different heads, you can see like what kind of interactions it's learning. Let's say you have a head that is associating traditionally like male, like masculine roles to like men, or like feminine roles to female, or something. Some heads that are learning some interactions. Can you drop those heads just completely and try to like after training and then debias models that way or something? Can you like inspect?
Probably you can, but I've seen a similar works where they would analyze the heads in terms of which one is actually useful for the model to learn. And then when you drop those heads, you're making the model much smaller and simpler without losing much of the performance.
How do you know what's useful?
But you can see which heads represent meaningful relationships.
Okay.
Right?
Through a similar kind of approach.
Yeah, because you have the pairs there, right?
Yeah.
So you can look and say, oh, this doesn't make sense, or
Yeah.
this actually doesn't learn much value. Maybe attention remains very stable across all pairs. Then it's going to be useful, right? You can do this kind of analysis and make the model smaller. Similarly, you can also say, oh, this model is not invasive, so maybe this attention is not useful. Yeah, remove that. I wouldn't be surprised. I haven't seen such work, but it might be useful.
Yeah.
Why not?
Cool. There's the paper before this actually showed that like the later layers, as you go down the layers, like it incrementally adds like marginally less information, or it seems to do less. So yeah, you can also just like trim the layers as well, like as well as the heads, right?
Cool. I'll end the recording.
Did I miss anything? Have we got any?